Right now, we're going to hear from Samuel Cochran, who attended Pratt Institute and received his bachelor's degree in industrial design in 2005. While at Pratt, Sam's academic work spanned sculpture, furniture, product, and transportation with a focus on innovation through the design process and an understanding of technology's possibilities through systems and objects. Sam has been the Chief Design Officer at SMIT since 2005 and took over as acting CEO in 2010. Please welcome Sam to the stage.
Thank you. So I'd like for everyone to take a moment to think about their electricity use. At some point today, you may have used one of these devices and powered it with a plug. Behind that plug are a number of sources of electricity, and 60% of those come from fossil fuels. 300 million years ago, this was the source of those fossil fuels. This is the Carniferous period when the Earth was covered in swamps filled with organic life rich in carbon. Over time and with pressure, that turned into fossils and now coal and other organic matter, or oil, natural gas, etc. We have been on a trajectory of burning this material because of its low cost, but really we're burning a material that came from this space and was powered by the sun. So I'd like to take a moment to just hold on to that thought and talk to you about our company. We're a company that is built on three different basic fundamental ideologies: sustainability, technology, and design. We use those three basic foundations to develop, manufacture, and sell product systems to people. To think about sustainability, today we utilize materials that we extract from the earth, just like that coal, create objects, engineer that into different objects that we use in our day-to-day, and then those end up in a landfill somewhere eventually. We at SMIT choose to try and break that one-way cycle and create a circular loop that allows for us to utilize recycled materials whenever possible, design upgradability into our objects, and try and make locally as often as possible. I'm going to talk a little bit about technology. So when thinking about the sun and technology, we typically think about a solar panel. Today, solar panels are often used in configurations like these. We look at technology from a number of standpoints. These are the basic embodied energy in various solar technologies. On the far left, you see mono and polycrystalline panels. And then on the right, you see thin film panels all the way to organic. So this is a graph of the embodied energy to make the material, and then also its output. So mono and polycrystalline are the best producing photovoltaic panels, while organic is a lower producing panels, but it has the ability to be manufactured with a very low energy cost. So we don't have to extract silica and basically create glass ingots that then get cut and put into a photovoltaic embodiment. We can actually take organic material that is photoreactive, extrude it onto a plastic substrate, and have it be completely recyclable without any toxins in it. So if we think about that sun, and so actually these are the space that we'll be working in. So when you think about that sun, and this is actually one of those thin film panels, when thinking about that sun and what captures energy today from that sun, we look at plants. And plants are able to take that abundant energy that's here every single day and turn it into energy that they utilize to create their own food. And plants also have this other ability. They are able to find the locations and really react to our environment in such a way that allows for them to survive. So this is actually ivy, and ivy has a unique capability of finding areas within nature, whether it's climbing up a tree to find more resources. We have taken that idea and applied it to solar technology. So here's one of our first products, Grow, which is a hybrid wind and solar device. Each photovoltaic leaf is an organic printed photovoltaic that's manufactured in a reel-to-reel printing process that utilizes very thin film materials to encapsulate that photoreactive material. We're also able to encapsulate a generator that is a piezoelectric generator, so that as each one of these leaves moves in the wind on the side of a building, we're able to capture electricity from that as well. This was actually funded by NCIA, which is one of the sponsors of this event. And in that time when we were funded, we had this idea, and we wanted to create a proof of concept. So we were able to create that proof of concept, patent it, and in that time also develop a system so that we could manufacture a version of this today. And that version, and just another aspect. So this was actually in the Museum of Modern Art in New York and was purchased for their permanent collection. It was a part of an exhibit called Designing the Elastic Mind. And so here you can actually start to see some of the other points that we bring into our design process. We have individual modules that allow for us to quickly skin a large building and have a standardized unit. And again, you're able to see that this is a reel-to-reel manufacturing process that would create a flat material, but we're able to die cut out the photovoltaic material so that it's able to orient itself in a better orientation for photovoltaic panels and solar panels. In the time of developing Grow, we were able to develop Solar Ivy. And Solar Ivy is a system of components that allows for us to be very versatile in how we interact with our space. So we have an element that attaches to buildings, and we can attach to existing buildings or new construction, a stainless steel mesh that then works to span that large area of a building, and then our photovoltaic materials live on top of that. So this becomes a module that can update and be can live with the advancements of solar technology. So as technology advances and as these panels reach the end of their lifespan, we can replace them with the newest technology, which, given the lifespan of a typical photovoltaic, that could be 5 to 10 years out or 20 years out, in which case the new technology that would be applied to this would be much more have a much higher power density, excuse me. When looking at this system is defined by the rules that ivy has and how it interacts with our building. No building location is the same, and just one second. We're missing a slide here, just bear with me. So we have embodied the rules of ivy into our mechanical systems so that they can react, they can orient themselves against the surface of that building, and depending on where that building is on the earth, there's a different angle of instance. And so each leaf has the ability to then be pixelated for color and for aesthetic qualities, but also be able to angle and rotate such that it's able to be at a normal for that given solar angle of that building's location. So here you're seeing a cycle through a software that we use to program Solar Ivy across the surface of a building. We then attach a genetic algorithm to this so that we can take analysis from that surface and have a genetic algorithm basically populate species, and I'll talk a little bit more about that with another software video. So with this, we're able to work with density, varying densities of a building to have the program of the buildings stay intact. So if you're covering a curtain wall where you have a glass view through a building, we can have varying densities so you maintain that view, and then have higher densities where the available light might be much higher. And this works on a residential scale, on a commercial scale. To give you a sense of power output, this is a 4 kilowatt system. This is a 8 kilowatt system. And to talk about pixelation and density, we can use the software to then have advertising capabilities happen within Solar Ivy. So we're able to pixelate each foundational leaf to have a sign. This is a zoomed in version of a Post logo. This is actually where our offices are in Brooklyn, the Brooklyn Navy Yard. That's our logo there. And you're going to see another video. We'll have to wait a second for of us using that in our software. Just one second. Okay. So here I'm going to talk a little bit about how we can really utilize that genetic algorithm to react to a building's location. So here is a project that we did with HOK Architecture. They're a worldwide firm, and they were looking at, this is a garden that's at a hospital where they're going to have a healing garden, and this is going to be really for patients to spend time and just recover. So they were looking at having this wall covered in solar ivy. And so we went through an analysis to understand what was surrounding that wall, ran the analysis through our software, and then our genetic algorithm arrived at this solution. So we have the possible solutions within our rules that were defined by ivy and some design constraints that were derived from ivy. And then we literally are discovering the solutions. We aren't designing them essentially, we're discovering them through this genetic algorithm. So I'm going to talk a little bit about our newer product that we just launched this year that comes again from the same foundational elements. So this is thin film solar. Now we're getting into another biomimetic material, which is tensile architecture, which were derived from tensile forms in nature, which are spider webs and things like that, and modern sail manufacturing. So tensile solar is the product that comes from those other influences with our foundational elements of design. Tensile solar is, again, a modular system of photovoltaic panels. They're reinforced to create a three-dimensional tensile surface, and those are defined by having compound curvature so that this membrane, this very thin material, can be static and not move when wind is on it. Kind of like that sail with the wind included. If the wind weren't there, that sail would be flapping. So in tensile architecture, you have to introduce those forces. One of the beauties of tensile architecture is its minimal use of material. It's typically using fabric and other membranes. So we're able to do this, again, with a software that allows for us to have many options available in it. We can cycle through different types of photovoltaic materials. So we're going through organic panels, amorphous silicon, and CIGS again. And you'll see that the form of this tensile object is not changing. When we go and, again, attach our genetic algorithm to this, we run an analysis of the site, and this is a localized constraint, so this could be a tree, it could be a building. We gather the shadows that would happen from that, and that gives us an analysis for that surface. We then create a generation of individuals that are possible solutions within the design constraints for that surface. So here we've allowed for 2 of those points to move. Where is it? 2 of these points to move here and here, and these points to move up and down. Now we are literally letting our genetic algorithm find the best solution for us. It's doing the kind of heavy lifting. We're able to take the best individuals from that first generation after our analysis, breed them, and then generate the next, and then their offspring become the next generation. We then analyze that generation and are able to, again, breed those and come to the next. We continue to do that until the change is minimal and we found the optimal solution. So again, this has many applications within our world, from point-supported umbrella-like shapes to carports, much larger structures where we are attaching these different tensile objects together to create much larger parking structures, and even in large tent enclosures. And it also has the ability to, again, you're seeing the versatility of our software here, where we're able to, again, change some of the bounds, change the size of our solar panels, and have many different possible applications for these objects. So really what we're doing is we're trying to transform our relationship to energy, our environment, and have these objects be something that can really find their way to maximize the potential energy in our environment. Thank you.
Sam, one question. I was curious, what do you think the results of these findings have? What do you think the effect it would be on a college community like Wake Forest?
I think that this really has the possibility to show that our traditional ways of thinking about a technology can be transformed by finding tools or utilizing tools found in the natural world, in the computer world in terms of genetic algorithms and the CAD space, and allowing us to get into the space where we don't know that there could be a real solution that reacts to our world, and that can close that gap between the functional and emotional possibilities that a product can have in our world.